Hi, my name is Prashant. I will be presenting our topic Communicating Sequential Process or CSP. What is CSP? In computer science, communicating sequential process is a formal language for describing patterns of interaction in concurrent systems. It's a member of the family of mathematical theories of concurrency known as process algebras based on message passing via channels. We come here to the introduction. CSP is a simple programming language designed for multiprocessor machines. Its key feature is its reliance on non-buffered message passing with explicit naming of source and destination process. CSP uses guarded commands to let processes wait for messages coming from different sources. Here we come to the model. Each process runs on its own processor. All communications between concurrent processes are made through message passing. CSP relies on the most primitive message passing mechanism, non-buffered sends and receives, explicit naming of source and destination processes. What are non-buffered send and receives? When a process issues a send, the system call does not complete until the message is received by another process. This is something like a synchronous process. It's also called a blocking send. When a process issues a receive, the system call does not complete until a message is received by the process, also called blocking receive. This is also a synchronous call that once till the process completing nothing gets executed till the next line. Now here we come to the fundamental CSP concepts. A CSP process is completely described by the ways in which it can communicate with its external environment and appropriates the most important first step in CSP process, choosing its alphabet of event communication. Now, what is an alphabet? The set of names of events which are considered relevant for a particular description of an object is called its alphabet. The alphabet is a permanent, predefined property of an object. It's logically impossible for an object to engage in an event outside its alphabet. For example, a machine designed to sell chocolate could not suddenly deliver a toy battleship, but the converse doesn't hold. A machine designed to sell chocolate may actually never do so, perhaps because it has not been built for it, or it's broken, or nobody wants chocolates. But once it's decided that chocolate is in the alphabet of the machine, it remains so, even if that event never actually occurs. This is a simple example of an alphabet. An appropriate set of atomic interactions for the world we are modeling sigma. The alphabet all events is written sigma. In CSP, events are assumed to be instantaneous, that is, the instant when an interaction is agreed. Now here we come to an example about alphabets. Now alphabets are denoted using in curly braces up down is 0 for a simple counter. These components together confirm an alphabet. The following are the examples: in.x, out.x, xft for a unit that inputs and output values of type t on one channel each. Here we come to the third example. For example, here you take a vending machine. We pay X amount to get a cheddar parmesan cheese and we receive a change.x. So these two are events and these two command we can define them as alphabets, where M is the set of money amounts, where W is the set of weights for a cheese shop. And here then there's another process called stop process. Now what is a stop process? The simplest of the process is stop process. Once the event is completed, it comes to an end. That process is called stop, just like an FSP. Stop performs no action. It is like a dead end. Can be convenient in specification and also provides a simple model for a deadlock system. So with the stop process, anyone can know that this is the last step in the process. So once there is stop, there won't be any next event going to take place. We can denote that by a simple example of a vending machine and how it works. In the case of vending machine, there are two kinds of events. Coin, the insertion of a coin in the slot of a vending machine, and the chocolate, the extraction of chocolate from the dispenser of the machine. In the case of more complex vending machine, there may be greater variety of cases. In 1p, the insertion of 1 penny. In 2p, the insertion of 2 penny coins. Note that each event name denotes an event class. There may be many occurrences or events in a single class separated in time. A similar distinction between a class and an occurrence spatially separated is as mentioned in the example. And here the example continues. Initially, the machine will accept the insertion of a coin in the slot, but will not allow a chocolate to be extracted. But after the first coin is inserted, the coin slot closes until a chocolate is extracted. The machine will not accept two coins in a row, nor will give you two consecutive chocolates. The simple vending machine that successfully serves two customers before breaking can be represented in CSP by this coin, coin, coin. Then we get a chocolate. Then again we insert a coin, we get a chocolate. So you're serving two customers and you get two chocolates. At the end, when you receive the chocolates, here we come to the stop state. After the stop says there is no continuation of the event until a new event starts. Similarly, we come to another example of a board game example. The simple board and a ball game where it has to move either up or right and it has to come to a stop state. Here if we consider the board game example here, the ball can either move up or right and then up because it can't touch the gray space. Here now we denote in CSP the way the ball moves, the possible movements of a counter on the board. And the possible movements of the ball and the counter you can define it by saying that's a process. If it goes up it will stop, and right, the still process can continue. Again you can go right, the process still can continue, and once you go up you come to a stop. Well, as the ball cannot move to the left or top or to the right because that is the end point of the ball of the game. And next we come to an important topic called mutual recursion. What is mutual recursion? A recursion permits the definition of a single process as the solution of a single equation. The technique is easily generalized to the solution of sets and simultaneous equations in more than one unknown. For this to work properly, all the right hand sides must be guarded, all the right hand side and each unknown process must appear exactly once on the left hand side. Drinks dispenser example it's called, where it's like a vending machine. You press on orange or you press on any coke or any other drink and you receive the bottle. But here I take an example of, we have a machine which gives you orange and lemon juices. Here the drink dispenser has two buttons labeled orange and lemon. The actions of pressing the two buttons are set orange and set lemon. The actions of dispensing a drink are orange and lemon. The choice of drink that will next be dispensed is made by corresponding button before any button is pressed. No drink will be dispensed. Here are the equations defining the alphabet and behavior of the process. The definition uses two auxiliary equations of O and L which are mutually recursive. And we can see the equations as mentioned earlier. Alpha dd equals alpha orange equals alpha L. Here we set orange, set lemon, orange and lemon. This considers these four components come out of the alphabet. As you can see, the dd equals set orange or set lemon. You can either set any of the things. O defines orange O, set lemon L, set orange O. Then again you come to the L, lemon O, or set orange O, or set lemon L. Informally, after the first event, which must be a setting in event, the dispenser is one of the two states O or L. In each state, it may serve that appropriate drink or be set in the other state. Pressing the button for the same state is allowed, but has no effect. By using indexed variables, it is possible to specify the infinite sets of equations. And we come to another important topic in CSP, it's called concurrency. Concurrency is the decomposability property of a program, algorithm, or problem into order independent or partially ordered components or units. This means that even if the concurrent units of the program, algorithm, or problem are executed out of order or in partial order, the final outcome will remain the same. This allows for parallel execution of concurrent units, which can significantly improve overall speed of the execution in multiprocessor and multi-core systems. I come to show a example. This is the dining philosopher example. A philosopher was expected to spend most of the time thinking, but when he felt hungry, he picked up his own fork and plunged into the spaghetti. Here, I use equations related to how the dining philosopher problem works. We shall now construct a mathematical model for the system. First, we must select the relevant sets of events for each philosopher. The set is defined as shown in the equation there, where modulus addition is the addition modulo 5 or so, and 1 defines the right-handed neighbor of the ith philosopher. Note that the alphabets of the philosophers are mutually disjoint. There is no event in which they participate jointly, so there is no whatsoever in which they can interact or communicate with each other. A realistic reflection of the behavior of philosophers in those days. The other actors in a little drama are five forks, each of which bears the same number as the philosopher who owns it. A fork is picked up and put down either by the philosopher or by his neighbor on the other side. The alphabet of the ith philosopher is defined as alpha fork, I picks up the fork, and modulo I puts down the fork, which modulo defines the subtraction modulus. Thus, each event except sitting down and getting up requires participation of exactly two disjoint characters, a philosopher and fork as shown in the diagram. So this is a simple example of how a concurrency and deadlock occurs in a CSP process, and the equations there shows you the events that take place. Thank you.